you very much. So let me start by thanking you all guys for inviting me and for giving me the opportunity to give this talk in this very nice series of seminar. So yeah, I will mainly talk about this Green's function, the retarded Green's function and its complete mode decomposition. And then towards the end of the talk, in the second part, I will talk about bouncing singularities and bouncing geodesics. So the talk is based on this series of work in collaboration with Ben Withers, also from University of Southampton. And in the first half of the talk, I will mainly talk about this first work, which is in collaboration also with Ben's PhD student, Javi Carballo. So let me start by introducing, let's say, the main character of this talk, that would be the retarded Green's function. So anytime you will see a capital G in this talk, it will be the retarded Green's function. And this is a key object in the context of black hole perturbations, because essentially, at least at the linear level, if we can reconstruct and having control analytically on the retarded Green's function, essentially we can say that we have solved black hole perturbations in principle, since if we want to reconstruct, for example, waveforms with a generic source, it is enough to just take the convolution of the retarded Green's function with the source itself, whether we can do it analytically or numerically. But the key point is really to start from the construction of the retarded Green's function. And for all the talk, I will focus on the case of spherically symmetric spacetimes. And the goal that I have in mind is to describe the asymptotically flat Schwarzschild case with some caveat or a small deviation from it that I will describe later. And moreover, we will deal with the retarded Green's function at fixed quantum numbers L and M, meaning that we will not consider the angular dependencies for the Green's function, but we will just work in time and radial parametrizations, so just in these two coordinates. And this also allows us to not having to deal with let's say, the additional difficulty of summing over all the quantum numbers and dealing with these divergences, but we will just focus on TR dependence. So with this setting, we can essentially define the retarded Green's functions in position space as the solution of the partial differential equation in Formula 1, where here the retarded Green's function is sourced by the insertion of two delta functions with insertion points T prime and R star prime, where R star is the tortoise coordinate. And the partial differential equation also depends on some potential that I'm denoting with V of R, that contains information not only on the black hole background that we are considering, but also on the specific type of perturbation. And I will be more precise later on which concrete cases we will be analyzing. And finally, the retarded Green's function obeys causal response, meaning that it vanishes for times that are smaller than T prime, which is the time in which the delta function is inserted. So now, to construct the Green's function in position space is not completely easy. So it is easier to actually start from a different perspective and to construct the retarded Green's function in frequency space. And this is just defined by Fourier transform with respect to the original retarded Green's function. And essentially, we are factorizing the time dependence just in the last exponential factor. And we are introducing some line integral that goes over the real line, but this is just shifted by a small amount in the imaginary direction. And then this G tilde function here is now a solution of an ordinary differential equation, a second order one, that is the one appearing in Formula 3, which is sourced by a single delta function, again, by at the same insertion R star prime. And this has essentially the same form as before, depending on the same potential and the frequency squared here, which comes from this factor over here. But now this G tilde is much easier to construct and to describe. And to construct it, indeed, we just need the homogeneous solutions to the differential equation 3 obtained by substituting the right-hand side just with a 0. And among all the local solutions that one can consider, there are some solutions which are preferred, let's say, by imposing some boundary conditions on the perturbations. And usually the boundary conditions that one consider are the presence of only ingoing modes at the black hole horizon, And we write this solution around the black hole horizon as phi in, which has this asymptotic behavior for r star going to minus infinity. So one thing that I can add is that the tortoise coordinate usually has a range which goes from minus infinity to plus infinity. Minus infinity is the location representing the black hole horizon. R star going to plus infinity, for example, in the Schwarzschild case, represents the radial infinity. And I will comment on it later again. And the other boundary condition or the other preferred solution that one can introduce is what we call the phi up, which is the outgoing solution at infinity. So given this set of two local solutions, the retarded Green's function g tilde can be constructed just by a radially ordered product of this phi in and phi up solution divided by their Wronskian. So the Wronskian is taken with respect to the r star coordinate. And if you look at equation 3, since there is no first order derivative in r star, this is just a constant in the r coordinate, but it depends on all other parameters in the game, and particularly it depends on the frequency. And indeed, this Wronskian is a quantity that vanishes when the two solutions are linearly dependent. And this happens for a discrete set of frequencies, which are called quasi-normal mode frequencies, and are really frequencies that are characteristic to the black hole spacetime one is studying. And also an alternative definition that is very clear from this argument for the quasi-normal modes is that these are just poles of the retarded Green's function. So the quasi-normal mode frequencies really play a key role for describing the retarded Green's function in frequency space. At what one can ask if we can actually reconstruct the retarded Green's function just by considering the quasi-normal modes as its poles. So the idea that goes back to Levers in the 80s is that we can start from the definition in equation 2, starting from the g tilde in the integrand for the retarded Green's function in position space. And we can try to use Cauchy theorem to actually reconstruct the original retarded Green's function just by taking the residues of the poles associated with g tilde, namely the quasi-normal mode frequencies. So to do that, we close the integration contour in the lower half plane, and we pick up residues from these black crosses, which are there for reproducing the quasi-normal mode frequencies. Also, let me stress that in the asymptotically flat case, the singularity structure in the omega plane is a bit more complicated, as it also involves a branch cut going in the negative imaginary axis. Here, I'm not showing this for a reason that will become clear later. But the idea is that essentially this is a picture that in principle enables to reconstruct the retarded Green's function in position space, and I can let's say I can write this prescription as in equation 7, meaning that the idea would be to reconstruct the retarded Green's function as a sum of three contributions. So the quasi-normal mode contributions, the branch cut, if it is present, computed by a discontinuity integral, and the large frequency arc. So the problem with this prescription is that since many times it is known that, let's say, the quasi-normal mode frequencies contribution is convergent at sufficiently late times, but at earlier times, some or actually all of these contributions can become infinite. And in particular, it doesn't make sense to sum infinite contributions to reconstruct a finite quantity as the retarded Green's function is. So the question now is, can we actually make sense of this decomposition at earlier times? Or when these quantities are infinite, can we replace them in some way so that we are actually summing just finite quantities to reconstruct the original one? And this is the kind of questions that I will try to answer in the first part of the talk. So for concreteness, as I was saying, the ultimate goal is to consider the Schwarzschild black hole, but we actually consider a small deviation from it, and we studied the Schwarzschild de Sitter black hole with a small positive cosmological constant. And first of all, I will comment on why this is consistent, or from here, why we can recover the actual flat solution. And second, I will describe in a moment why this is an advantage. But let me start just by presenting the formula that we need. So first of all, in equation 8, I'm writing the metric of this four-dimensional Schwarzschild de Sitter black hole, where the last term represents the round metric on the two sphere. And f of r is the blackening factor, which depends on the mass of the black hole and the positive cosmological constant. These two parameters are also, they must also satisfy these inequalities, and this is to ensure that the space-time has the correct horizon structure. And indeed, this structure can be read from the zeros of this polynomial equation Rf of r equal to 0, which admits within these assumptions three real roots. So one of them is a negative root, and we denoted it with r minus. It's just some unphysical solution. Then there are two positive real roots. The smallest one is representing the event or black hole horizon, whereas the biggest one is the cosmological horizon, which is larger than Rh. And we are denoting it with R plus, and both R plus and R minus can be written in terms of Rh and the cosmological constant as in equation 9. So one thing that we can already see from here is that in the limit in which lambda goes to 0, from the metric we recover precisely the metric of the four-dimensional Schwarzschild black hole. And also these R plus and R minus, they both go to infinity in different direction, meaning that R plus goes to plus infinity and R minus to minus infinity, but essentially they will represent, let's say in the complex R space, the same point at infinity. And this will be important for the Schwarzschild solution. And then, having described the background we are considering, we go to describing what are the linear perturbations that we consider on top of it. And again, it is easier to start just by considering a Fourier mode decomposition for the perturbation fields. Namely, we are factoring out the angular dependence in terms of spherical harmonics, since we just have to deal with spherical symmetric backgrounds. And all the non-trivial information is encoded in the radial dependence, and the radial part just satisfies a second-order ordinary differential equation, which here it's written in terms of the R variable, but if you rewrite this in the R star variable, it has precisely the same form satisfied by G tilde that we saw before, with a 0 in the right-hand side. And the potential is assuming this expression, we are considering this kind of potential that depends on the angular quantum number L. And there is one more parameter in game, which is spin S. And indeed, with a single differential equation, we are actually encoding three different kinds of linear perturbations. So for S equals 0, we have a conformally coupled scalar field. For S equal 1, we have massless electromagnetic perturbations. And for S equal 2, we have Regge-Wheeler or vector type gravitational perturbations. So from here, if we study the singularity structure of this differential equation, it is easy to realize that this is a Hoyne differential equation, meaning it is a Fuchsian differential equation with four regular singularities. And these singularities are located at R equals 0, and then the three horizons that I described before, so the black hole horizon and R plus, R minus. And as I was saying, in the limit in which lambda goes to 0, R plus and R minus, they both go to infinity, meaning that we can also consider the same class of perturbations on top of flat Schwarzschild. And in the limit in which lambda goes to 0, the differential equation will become a confluent Hoyne equation, having an irregular singularity at R equal infinity. So this is an important point because in this slide, I will just mention briefly what we did in this talk, in this paper, sorry. And the idea is just that the presence of an irregular singularity is actually what causes the presence of the branch cut in the omega plane in the flat solution. But actually, if we turn on a positive cosmological constant, this branch cut is replaced by a set of quasi-normal modes, which are spaced by the small cosmological constant in the game. And we call this family of quasi-normal modes that essentially discretize this branch cut de Sitter modes, just because, as you can see from this expression 13, which is just an expansion in powers of lambda, the leading order is precisely the same expression that would appear for the exact quasi-normal mode frequencies in pure de Sitter spacetimes. And what we showed in this work is that if we take the contribution of these modes in the retarded Green's function of the Schwarzschild de Sitter solution, in the limit in which lambda goes to 0, we can actually reproduce the late time price law tail. So this tail that is there for the same class of perturbation in flat Schwarzschild, and it is a late time polynomial decay of this form, as in equation 14, meaning that all the key features of the flat solution can be recovered by turning on this positive cosmological constant, and everything is consistent also at the level of the boundary conditions that I didn't specify. Indeed, if we turn on this cosmological constant, as I was saying, we are introducing a new horizon, which is the cosmological one, which is larger than the black hole horizon, and the region between the two is really the region where scattering processes take place. And so we usually impose outgoing boundary conditions at the cosmological horizon, and in the limit in which lambda goes to 0, this is actually going to R to infinity, and the boundary conditions between the two situations are consistent. So this is just to show that essentially by turning on this small lambda, we are not losing any information on the ideal situation of asymptotically flat Schwarzschild. But now let me come to the key advantage, that is what I showed essentially what I showed in this result, that is saying that if you remember the schematic picture of the retarded Green's function as a sum of 3 terms, now we are effectively encoding the branch cut inside the QNM family, because we are discretizing the branch cut with this set of quasi-normal modes in the de Sitter situation. And so we are actually reconstructing the retarded Green's function just as a sum of 2 contributions instead of 3. And so to consider divergent and convergent quantities, we can just restrict to these 2 families of contributions. So now the idea would be to consider when the arc is either finite or it is divergent. And this is kind of easy to guess just by looking at the original expression of the Green's function as an integral over the frequencies. And in particular, we know that the in and up solution that I was introducing before at large frequencies are well approximated by plane waves, so we can study the exponential behavior of this integrand, and we can see in which region of spacetimes the integrand is exponentially divergent or exponentially decaying, so that we can actually have an idea of where where the arc will vanish, giving a convergent sum of Q and M's, or where the arc is becoming divergent, and so is also the sum over quasi-normal modes. So in that situation, if we want to change the exponential behavior of the integrand, the key idea was to use a connection formula, namely to re-express one of the 2 solutions appearing in the integrand in terms of linear combinations of a basis of local solutions around the point where the second boundary condition is imposed. So the idea here, and I'm choosing to re-express the in solution at the black hole horizon in terms of a linear combination of a basis of solutions phi up and phi down, which are defined as ingoing and outgoing modes at the cosmological horizon, so at the other boundary, let's say, of our boundary value problem. And this analytic continuation is mediated through 2 connection coefficients that I'm denoting with C in up and C in down. And the key idea here, and why I stressed before the fact that the perturbations we were considering are within the Hoyne class of differential equation, is that there have been many developments recently about the connection formula for Hoyne equations. And in particular, these solutions are just written down in terms of Hoyne functions. And we have, thanks to techniques coming from Liouville conformal field theory and n equal to 2 supersymmetric gauge theories, some very concrete and combinatorial expressions for these coefficients that allow us to study also their singularity structure. So the advantage of using this connection formula on top of, let's say, changing the exponential behaviors of this integrand is also that if we actually substitute this solution with these 2 terms over here, we are splitting the full G tilde expression in a sum of 2 terms that we call G tilde plus and G tilde minus. And we can study the analytic structure of the 2 terms separately. And so let me describe more precisely what is the form that these 2 terms have. So first of all, as I was also writing over here, the integrand depends also on the Wronskian between the 2 solutions. But if you use the expression here in the right-hand side, you can easily realize that the Wronskian between phi in and phi up is just proportional to the connection coefficient in front of the discarded local solution at the cosmological horizon. And this is just because taking the Wronskian between these two terms, these are just linearly dependent. So the Wronskian is actually proportional to one of the two connection coefficients. And when we substitute this expression inside here and we use this fact, we can realize that up to some other terms which are not important for the analytic structure, G tilde plus is proportional to the product of two up solutions, and it contains the ratio of the two connection coefficients, whereas G tilde minus is just proportional to the product of one up solution and one down solution, and the connection coefficient, let's say in the numerator and in the Wronskian, are the same so that they simplify. And now for the singularity structure, this is the picture to have in mind. So on the left-hand side, I'm representing the full structure of G tilde, having only quasi-normal modes as its poles in the lower half plane. Now in G tilde plus, we still have this factor in the denominator, which has zeros at the quasi-normal mode frequencies. So the quasi-normal mode frequencies are still poles of G tilde plus, but they are not poles of G tilde minus. On top of that, we have new singularities that appear, and these singularities all lie on the imaginary axis and are located at Matsubara frequencies. These are just imaginary integer multiples of the surface gravity associated to the horizon around which we are performing the computation. So here, as I was saying before, at this level, I had a choice to make. So I could either re-express the phi in solution in terms of the other two solutions at the cosmological horizon, or doing the opposite and re-express phi up in terms of solutions phi in and phi out around the horizon. Here I'm making this choice by assuming to be in this regime of, let's say, to be on the right of the insertion of the delta function. And so I'm performing the computations around the cosmological horizon. This is why these are the frequencies that appear that are proportional to the temperature at the cosmological horizon. But the key fact is that these singularities appear both in G tilde plus and in G tilde minus in such a way that the residues in the two terms are opposite to each other, so that when you sum the two contributions against each other, they vanish in the full G tilde function. So G tilde does not see these singularities. These are just singularities of the single pieces once the Green's function is splitted by using this connection formula. But now having this structure allows us to essentially close the integration contour, as I was doing before, in different ways according to which region of spacetime we are considering. And so the prescription that we proposed is the following. So I will be more precise in a moment, but for now, let me use just the wordings late time or early time because it's easier. So there will be one region, which is what we call region 1 at late time, in which the quasi-normal mode sum is convergent and the large frequency arc in the lower half plane is exponentially decaying. And in this situation, we can close both terms G tilde plus and G tilde minus in the lower half plane. So we will be picking up residues from the quasi-normal modes, which are poles of G tilde plus. And the contributions from the negative Matsubara frequencies will just cancel out when summing the two terms. So with this prescription, essentially, we are recovering the same picture that I showed you before, already going back to Lever. But then there is another situation earlier, so at earlier times, that is what in this region that we call region 2, in which the sum over quasi-normal mode is divergent, and also the large frequency arc in the full G tilde is divergent. And in this case, we close the contour in a different ways. In particular, we close the contour for G tilde plus in the upper half plane, picking contributions from the positive Matsubara frequencies. And we close the contour in G tilde minus in the lower half plane. Notice that since one of the two is associated with positive frequencies and the other one with negative frequencies, these two contributions do not vanish when summed with each other. But actually here, the arcs in the single contributions, they are both going to zero, so that we are effectively describing the retarded Green's function in this region 2 as a sum over Matsubara frequencies only. And finally, there is a third situation, which is a bit more trivial, that is outside the light cone where the retarded Green's function is supported, and is what we call the region 3. The retarded Green's function is just equal to 0 by definition, and indeed we can recover this just by closing both terms in the upper half plane, and the arcs in this region, they both go to 0, and the contributions from the positive Matsubara frequencies cancel with each other. So in the region 1 and region 2, where actually the Green's function is non-zero, the formula 24 is a bit more quantitatively, although in terms of an unknown function for the moment, is expressing what I mean by late time and early time. And this is the condition involving the time and tortoise coordinates for the insertion of the delta function and for the observer. And then they depend on this new quantity, R star bounce, which essentially is expressing the location in which this light ray originates, this light ray which is bounding the region 1 and region 2. So before coming to this R star bounce, this is the picture that we can reconstruct by applying this prescription. So here we are plotting, let's say, two different quantities. So in black, you can see just the numerical solution obtained by solving the partial differential equation for the Green's function in position space. And we are approximating the delta function with a Gaussian narrow and peaked. And this just gives the black function in the picture. And then with different colors, we are denoting region 1, 2, and 3 that I just introduced. In region 1, we are just writing the sum over quasi-normal mode residues. And here we are including the first 6 quasi-normal modes of axis and 6 quasi-normal modes, let's say, from the de Sitter modes on the negative imaginary axis. In region 2, we are instead considering the contributions from the Matsubara frequencies, 30 Matsubara frequencies in the upper half plane for G tilde plus and 30 in the lower half plane for G tilde minus. And the plot already shows very good agreement for this reconstruction. And this line over here essentially denotes the position of, so it's related to the position of R star bounce, which is the one limiting the two regions. So to compute this R star bounce, we took let's say, the easier from the analytic viewpoint of the contributions, meaning since we know the analytic expression for the Matsubara frequencies, we can just take the residue sum over G tilde plus at these positive Matsubara frequencies and just perform a ratio test. So this was just to get some approximate value for R star bounce. We also did some numerical check directly in the asymptotically flat solution, and we had a taste of what the result should be. But the idea is that this R star bounce seemed unrelated to, for example, the peak of the potential, as we were expecting in the beginning. It seemed unrelated on the type of perturbations we were putting on top of the space-time. And also, for example, it seemed independent on the quantum numbers. So the question that arises from here is, is there a geometric origin for this R star bounce? Or let's say, rephrasing the question, what is actually describing this region of convergence of quasi-normal modes? Can we really make a sense of this R star bounce quantity? And it seems kind of a joke, but actually it is not, and it is really how things went. We started to think that this name bounce that we gave to this quantity had something to do with some recent developments that were going on in the context of bouncing geodesics and more in the ADS CFT community. And indeed, the first thing was to realize that these bouncing geodesics that were analyzed in Schwarzschild ADS solutions they do exist also in the asymptotically flat Schwarzschild black hole, meaning that if you take the maximally extended Penrose diagram of the Schwarzschild black hole, there exists this limit of radial space-like geodesics that connect the two external regions, and these are just made of two null lines in the diagram, and they bounce either at the future singularity, the black hole singularity, or at the past or white hole singularity. And I will just now show how one can realize the existence of these bouncing geodesics, but these are closely related to this R star bounce location that here we are just drawing pictorially in this way. So indeed, one can start by considering a radial space-like geodesic in TR coordinates, which obeys the equation 26, where here the dot just denotes the derivative with respect to these affine parameters lambda. And since dt is a killing vector, there exists a conserved quantity along the geodesic, which we call the energy, that is just this form over here. And in terms of the energy, you can study, first of all, the turning point of this radial geodesic, meaning the point that has minimum radius along the geodesic. And this has a dependence on 1 over e squared, so that in the large energy limit, this just goes to 0, meaning that these geodesics approach the black hole singularity. And also you can study this quantity to have, let's say, the behavior in the TR plane. And it is easy to realize that in the limit in which e goes to infinity, this quantity that just goes to plus or minus 1 over f of r, the blackening factor, so that once you integrate over r, essentially you recover that the large energy limit of these families of geodesics just approach the two branches of null curves that I showed you in the previous picture with constant u and v, which are just sums and difference of t and r star. And therefore, the limiting objects are precisely what I was describing here, this union of two null lines bouncing either at the black hole singularity or the white hole singularity. And now, the other realization is that the retarded Green's function by itself has a distributional nature, and it is very easy to realize this just by, as the first equation that I showed you, since this is essentially sourced by a delta function, which is the easiest example of a distribution. And the singularities in the distributional sense of these quantities are governed by the standard Hadamard theory, or more precisely, there's this theorem about propagation of singularities that says that the singularities essentially propagate around along B characteristic curves on the geometry, which in this case are just null geodesics of the geometry under scrutiny. And this is exactly the same picture that is present in the Schwarzschild ADS black hole. So here I just took this figure from this seminal paper where these bouncing geodesics were studied in the context of planar Schwarzschild ADS black holes. And it was realized already back then that the existence of these bouncing geodesics was related to the existence of some of what were called bouncing singularities, that are singularities at complex time of some analytic continuation of the retarded Green's function by allowing time to have values in the complex plane. And now, so we can come back to our original question and asking how is this related to the quasi-normal mode convergence region? And we can now really focus on the asymptotically flat case. And we can study the quasi-normal mode contribution to the retarded Green's function, which has this form in equation 30 that just depends on the sum over the frequencies, and Cn are just the residues of the retarded Green's function at these frequencies. And to actually study the behavior of this series, it is enough to study the large overton number behavior. And in particular, this is very well known just from WKB computations. So the large overton numbers at leading order just appears in front of the imaginary part of the frequencies, where here beta is the inverse temperature at the black hole horizon. And then there are subleading corrections involving also the real part for these frequencies. So if we just insert this leading order expression inside this exponential here, it is easy to realize that this contribution can just be rewritten as a power series in a new variable that we called capital X, which is this variable involving the exponential of the original time coordinate. And being a power series, the radius of convergence of this quasi-normal mode series is just fixed by the closest singularity in the complex X plane to the origin X equal to 0. So to come back to the geodesic structure that I was defining before, we can really describe quantitatively these null geodesics. And the easiest way to do it is to go to Schwarzschild coordinates. So using the exponentials of the small u and v that I was defining before and defining these quantities over here. And for concreteness, I'm also writing down the r star coordinate with, importantly, the dependence on the integration constant that I'm calling C. So we start from a point in the first exterior region, UR, VR, and then it is easy from here already to write first the two direct light rays emanating from this point, which are just at constant V equal VR, and the other one would be at constant U equal UR. And then the intersection of these first, let's say, light ray with the future singularity is determined by this system over here, where U times V equals to this exponential involving C is representing the position of the black hole singularity. And so the equation for the first bounced light ray is constant U equal to this value over here. And in the same way, as I was saying, we can also write the expression of the second bounced light ray from the white hole singularity, so from the past singularity, which has this constant V expression over here. So essentially, in the end, we have four singular loci which are governed by this theorem of Hadamard, which are two at constants U, the first representing a direct light ray, the other one a bounced light ray, and two at constant V. And we can re-express these singularities in terms of the x coordinate that I introduced before. And this is the expressions that these singularities take in the complex X plane. Two of which, the ones related to direct light rays, are positive, two of which are negative. And so if you remember that x is just the exponential of some, so it depends on the exponential of time, it means that the last two singular points in the x plane are associated with some complex value of time, whereas the first two are associated with some real value of time. And in particular, again, the region of convergence of quasi-normal mode is set by the singularities, by the singularity which is closest to x equal to 0 in the complex X plane. And it turns out that anytime this singularity is of a bouncing type, so it is not real in the t variable, but it is complex and it is associated with a negative value of x. So this is the picture, let's say the resulting picture to have in mind. In particular, there are two situations which are described here. So let me start from the right panel, which is more similar to the situation of Schwarzschild de Sitter that I described before. So this is the case in which, so the R star bounce location is precisely this integration constant C over here. And this is the location in which the insertion point of the delta function is to the right of this bounce location, and the observer is also to the right of the insertion of the delta function. And this is essentially the same picture that we had in the figures that I showed you before. In this case, the quasi-normal mode convergence region is set by the future bouncing singularity. And then there is another case, which is the one in which we are to the left of the bounce location, and the observer is closer to the horizon with respect to the insertion of the delta function. And in this case, instead, the quasi-normal mode region of convergence is set by the past bouncing singularity. So in both cases, it is set by the bounced light rays and not the direct ones. Then the other thing is, on top of this disk in the complex X plane, here I'm also representing the region of convergence for the Matsubara mode that I was describing before. But here there's some explanation that I have to give you, because before the situation that I was representing is this one. But it actually happens that the Matsubara frequencies at the cosmological horizon that I was describing, they all go to 0 in the limit in which lambda goes to 0, because the temperature at the cosmological horizon goes to 0 in that limit. And effectively what's happening is that the sum over these Matsubara residues also has to be changed into some branch cut discontinuity integral. So we didn't perform that computation. But what remains finite is, or what remains is the existence of a Matsubara mode decomposition in the near horizon region. So the Matsubara modes associated with the black hole horizon temperature, they remain finite and discrete in the lambda to 0 limit. And this is the computation that I now show you to see that the bouncing geodesics are responsible also for the region of convergence of the Matsubara modes that I introduced before. So this is the expression for the Matsubara frequencies associated with the horizon temperature, where k is just a mode number labeling, let's say, their position on the imaginary axis. And the idea, as I was saying before, is just that to actually see them appearing in the retarded Green's function, we use again a connection formula, but that is in the opposite direction to what I wrote before. So we are expressing the outgoing solution at infinity, or what before was the cosmological horizon, as a linear combination of ingoing and outgoing solution at the horizon. But the situation is basically the same. That is, we are still splitting the G tilde function in a G tilde plus involving the ratio of the two connection coefficients, and the G tilde minus that is just proportional to the two homogeneous solutions. And now, for the Matsubara mode, if you remember, we close G tilde plus, we close the integration contour of G tilde plus in the upper half plane, and the integration constant contour for G tilde minus in the lower half plane. So in the upper half plane, we are taking then the contributions from the positive Matsubara frequencies, which have an imaginary part which is of opposite sign, for example, with respect to the quasi-normal modes that I was analyzing before. And this is why G tilde plus effectively becomes a power series in powers of the inverse of capital X, whereas G tilde minus is similar to the situation of quasi-normal modes, and it is still a power series in powers of X. But putting the two together, essentially they form a Laurent series, and this is why we expect an annular region of convergence instead of just a disk. So we can start with the computation of G tilde plus. Here I'm skipping many details, but essentially, again, we can just restrict to consider the large K behavior of the series, and we can write some approximate values for the asymptotic residues at large K, which admits these values over here. And the sum over these asymptotic residues can be performed exactly, and it is proportional to a logarithm. In particular, this leads to a logarithmic singularity, which is precisely set at the past bouncing singularity location. So this fixes the inner radius of the Matsubara annulus region of convergence, and in particular, it really coincides with the singular points that was fixing the convergence region for the quasi-normal modes. Similarly, we can perform the same computation for K becoming large but negative for the G tilde minus term. And again, we can play the same game, summing the asymptotic residues. Again, we find some logarithmic function approximating this sum. And this time, the logarithmic branch point over here is not of bouncing type, but it is really associated with a direct light ray. So it is associated with the ingoing light cone singularity. And this fixes the outer radius of the Matsubara annulus. So in total, we have this singularity for the G tilde plus contribution and this other one for the G tilde minus. And the region between these two circles is the annular region of convergence for the Matsubara modes. So going to the conclusion, so what I tried to present in this talk was starting from the idea of constructing the retarded Green's function by considering its singularity structure. And originally, the apparent singularity structure only involves quasi-normal modes. But if we naively take the quasi-normal mode sum and try to reconstruct the retarded Green's functions from them, we do not recover a convergent mode sum everywhere in space-time. And the situation is improved if we split, let's say, the integrand of the Fourier transform of the Green's function, and we split the quantity that I call G tilde in two contributions. And we find that the singularity structure is actually more involved if we consider the two splitted terms. And we introduce this set of Matsubara poles, with which we can reconstruct the retarded Green's function precisely in the region where quasi-normal modes fail to describe it. And moreover, the light ray which separates the two regions of convergence is associated with this R star bounce location, which was quite mysterious to us in the beginning, but we just realized that it has a very clear geometric origin, which has its roots in the existence of these bouncing geodesics. And so the singularities that are actually fixing the region of convergence for quasi-normal modes are the bouncing singularities precisely that are precisely the relatives of the bouncing singularities present in the ADS black hole cases. And these are responsible not only for the region of convergence of quasi-normal modes, but also for the Matsubara region of convergence. And so with this, I finished, and I thank you very much for your attention.